Hello, everybody. It's about time. Let's start the lecture 11 on statistical foundation of reinforcement learning. Today, we're going to be um, finishing the topic on exploration. I'll cover the remainder part of the analysis on the linear MDP. And then we're going to move into a brand new chapter on offline reinforcement learning, which is more recent than more recent topic and more actively developing unfolding research area, and I'm hoping to cover some of the recent excitement about this setting and some of the things that we know, and then start with um, some models that are simple. Okay, so uh, first of all, I wanted to go over some of the logistic notes. The midterm milestone is supposed to be due today. If you haven't made progress on writing like a short 1-page or 2-page report on what you have been doing, what is your plan before the presentations, and what are your progress and so on. So you should write it up. It doesn't need to be detailed. Similar to the project proposal, this will be just a few sentences summarizing what each member of your team had been doing on the project, and it is important for me to look at them like as soon as you submit them on Gradescope. So similar to last time, just submit it as a PDF document. I'll go over them. I'll leave comments once I read your midterm project milestone, right? Another thing is regarding homeworks. So there are a few of you who haven't submitted the homework one. So even though there are no deadlines for the homework, so if you keep everything towards the end of the quarter, then it will be difficult for you to catch up, right? So the baseline for homework one is that it is a tough homework, and it is also somewhat long. So for those who are having trouble with homework one, you shouldn't feel bad, right? Because it requires you to not only understand the lectures, but also extrapolate a little bit in order to solve homework one, right? So it is a tough homework, and they are it's compounded with the issue that the first 3 questions are what I got from Wen and Xiang, who was running the concurrent course on the same topic in Cornell and University of Washington, and some of the homeworks has typos that might have affected your understanding. Yeah, so taking all these into consideration, yeah, so I think if you're still working on some homework one and you're finding it hard to allocate more time to work on it, you should just submit that everything you have, and if you don't have the full solution, submit the partially worked out solution to Gradescope. I'll just grade them as is, and depending on what it looks like in the end, so I'll consider adjusting the grading criteria for homework one, and potentially say use the best 3 questions out of all of them, and do a max pooling for everybody so that you get a reasonable evaluation for homework one, right? And homework 2 had been released for a while, and it is not as long as homework 1, and so start doing homework 2 if you haven't. You will see that it is probably easier than homework 1. Yeah, homework 1 is somewhat long because we covered a lot of materials, including the just MDP themselves and the generative model part of it. So it might appear to be a big jump from homework 0, which is supposed to be just a refresher of your prior knowledge, right? Toward at the end of the day, like it is you who is practicing these theoretical hammers in these homeworks, and once you can wield these hammers, then you have officially learned how to make use of these tools and techniques to solve new technical problems in the future, right? So they are like good problems to work out eventually, but if you can't finish them in time, that's perfectly fine. Like this is a graduate level course, and the hope is for you to pick up tools that are needed for you to conduct PhD level research. So you could take your time, but do submit what you have, because at the end of the day, I'm gonna have to still be the person who assign a letter grade to you. Like there needs to be some factual evidence that I do things at the end of the quarter. If you haven't submitted anything towards the end of the quarter, then it will be difficult for me to give you a say a letter grade of B and or above and things like that. All right, so I hope that explains everything. So these homeworks, they are challenging problems for you to learn a little bit more beyond just the lectures, and it sometimes require you to extrapolate the knowledge that you learned from the lectures. So that is the reason why they are challenging, and that is also the reason why that if you work them out, then you will really internalize these ideas and these methods, so they become truly yours. All right. Okay, in the last lecture, we talked about linear MDPs. So linear MDPs is a particular model that allows us to deal with extremely large state space and action spaces. We talked about properties of the linear MDPs. And interpretation of the assumptions and why some of those assumptions are needed, and why they can help us to write down Bellman equations in the way that we did. And we'll revisit some of these properties today. And we talk about the generalization of the UCB value iteration algorithm, also known as the optimistic version of the value iteration for the tabular Markov decision processes. We generalize this to the linear MDP setting. So after stating the algorithm and explaining the intuitions of the algorithm, we made an attempt to use some of the elements of the regret analysis that we have learned from the tabular UCB VI and from the linear bandits analysis by combining them and with optimism and simulation lemma and so on. Like we were able to prove the regret of linear MDPs and show that the regret is proportional to square root of n, where n is the number of episodes that you run. So which means that this algorithm is a no regret learning algorithm. What we left as holes in this regret analysis are some of the key lemmas that we didn't carefully prove. In particular, like the lemma about the uniform concentration. So this is a Hofstad's inequality, like inequality, but we need a high probability event to simultaneously apply to a continuum of functions satisfying certain properties, so that it can cover all possible choices that the algorithm could have come up with. So this is not something that we have dealt with. And at the end of the last lecture, we talked about an argument called a covering number argument that allows us to discretize the space and then apply the same old union bound argument to derive the uniform concentration. Right, so we'll get into more details about that today and formally prove everything that we have had left unproven in the first part of today's lecture. Okay, so as a quick recap, like we started off by motivating the study of linear MDP by saying that, well, we want to handle an exponentially large state space, and how do we deal with that? we need to come up with features, right? So for every state variable, an action variable pair, we can convert it into some feature map of S and A, right? And then there is a theoretical question, is that what are the assumptions that we need to make about this feature map so that it can allows us to efficiently learn the Markov decision processes, to, in other words, to learn the optimal policy. Like, does this suffice to assume that we have access to some function class, let's say, exists some theta such that theta transpose phi of SA is equal to Q star of SA, right? If this is the case, then learning theta allows us to learn the optimal policy, right? Because the optimal policy would be arc max of theta transpose phi SA. If we know theta, then we learn the optimal policy. But it was shown previously in the Du Kakade Yu-Xiang lower bound that this alone like isn't sufficient for us to, like, even if it is linear, if we weaken this assumption a little bit by saying that, well, even if this is smaller than epsilon, like for really relatively small epsilon on the order of 1 over square root of d, this is still impossible, right? This is still so you'll have an exponential lower bound saying that any algorithm is not going to be like have polynomial sample complexity in learning this MDP. And if we make this stronger by saying that for each policy pi, there exists pi star such that Q pi is equal to some pi star transpose this feature map phi of SA, right? SA. So this assumption is like a strengthened version of the approximate linear assumption is also not enough for us to obtain the polynomial sample complexity. So this is also not possible. So I talked about these two black question marks and whether assuming only Q star SA being exactly linear being still open problem, and even like it was stated to be an open problem from this 2019 paper, but in the past week I discovered that this open problem had been resolved. So people had proven that there is an exponential lower bound for this setting as well, right? So this setting is also like not tractable, right? So we need to make something that's even stronger than assuming the Q star function being Q star function being linear, right? So one possibility to assume that for all possible policies, then Q pi function is exactly linear, right? So this is assumption that it's still open. It is unclear whether in the online reinforcement learning setting whether this is sufficient for us to obtain the efficient learning with polynomial sample complexity in all parameters. And it was proven that this is sufficient in the generative model setting. So in that case, you can actually learn things easily. But whenever there are need to explore, and in a full reinforcement learning setting, this is still an open problem, right? So these impossibility results motivated authors like Jing and all to consider the even stronger assumption than the assumption of Q pi function being linear. So they made this assumption called linear MDP, which is a model-based approach by making an assumption that this transition kernel of the Markov decision process is actually factorized into two pieces. The first piece, just give me a second. All right. Yeah, it factorized into two pieces, and this is a model parameter, and this is your feature. So if we consider this this transition kernel, which is can be thought of as a matrix of size S by S times A. Okay, when this is an infinitely large matrix, what this assumption is saying that is we can factorize this matrix into two pieces, um, and this is your phi function. This is your feature map, which is assumed to be known. And in the intrinsic rank is D. So this is essentially a low rank assumption on the transition kernel. S by A, and this is S dimension, right? And this is a mu star. So to say it differently, linear MDP is really a non-parametric model because we're not making assumptions about we're not really making assumptions about all parameters of and we can never really observe enough samples for us to estimate this this mu star sufficiently well. So yeah, instead of non-parametric, it's actually a semi-parametric model where part of this is parametric, but we need to learn the relevant part of the parameters while not suffering any losses from being unable to have sufficient knowledge about the true model parameter that generates the data. Right. So this is so S can be exponentially large. That's why like the goal of linear MDP is to learn the optimal policy with a number of trajectories or number of samples that are polynomial in all other parameters and independent to the size of the state space, action spaces. Okay, so we talked about this algorithm called upper confidence bound value iteration algorithm for linear MDPs, which first solve the hypothetical ridge regression problem and get a sparse estimator of this. So notice that this can be efficiently represented because the optimal solution of this optimization problem is only supported on those coordinates where you actually observe actually have this observe the state. Therefore, you can use this to efficiently represent the solution. Yeah, and the reason is because no matter what you put in those S that is not observed, is not going to affect the objective function. In fact, you should always choose it to be 0 because you're penalizing those coordinates. Like if you choose them to be non-zero, then this value will be strictly larger than 0 and it becomes suboptimal. Right. So you can see the sparsity of the output by just observing the optimization problem. And then the idea follows from the same UCB VI for the tabular MDP that we want to run the optimistic value iteration by interlacing these exploration bonuses in the value iteration steps. And then after every episode of data, we update the policy into the greedy policies that's output from the optimistic value iterations. Okay, and the theorem says that if we choose those parameters, if we choose the regularization parameter of the ridge regression lambda to be 1, and if we choose this beta parameter, right, choose this beta parameter, which is exploration bonus, to be this like somewhat more complicated quantity, but mostly like polynomial in HD together with some logarithmic factors, then these together they yield a regret bound of they yield a regret bound that is a square root of in n. So this is number of episodes. This is a dimension of the features. This is a planning horizon of the MDP, and nothing in the regret bound depends on the size of the state space and action spaces. Meaning that they could even be they could be large, and they could even be a continuous space. Okay, so one particular design of this exploration bonus is coming from like you have seen this from linear bandits, and this is the this is the corresponding ellipsoid distance of input feature at a given SA measured by this quadratic form, and this lambda is equal to the sum of mu of SI AI actually SHI AI SHI AI transpose, right? So each one of them is a matrix. So this is a matrix of RD by D, right? So basically the unnormalized covariance matrix plus lambda identity with an additional terms that are coming from the regularization. All right, so this is the distance. This is the width of this data point measured in the natural ellipsoidal geometry that's described by the sequence of observations that are spun up by the by the algorithm itself. And beta is a multiplicative factor that makes it a little bit bigger, so that we can ensure that adding this is sufficient to give us optimism. Okay, and then we went over the steps of the regret analysis, which it succinctly summarizes in these two steps. The first step, we try to bound the regret for running episode episode little n, and then in episode little n we run a particular policy that's selected based on the data collected up to episode n-1. And so this is the right notion of per episode regrets for episode n, right? And by optimism and simulation lemma, and we have reduced the problem to reduced the problem to bounding like this complicated looking this complicated looking quantity. So this quantity is really like the key quantity of interest that we'll be addressing today, right? So we've stated the lemma to show that this quantity can be can actually be bounded by the by the exploration bonuses as well. So essentially we can bound this by the same exploration bonuses, and that shouldn't be surprising because that's exactly why we're choosing this, how we are choosing this exploration bonuses to begin with to ensure optimism, right? And one thing to point out is that this is a data dependent quantity. And this is a data dependent quantity because the because we actually use the same data that's up to this step to create this estimator for estimating this value function into the future, and we are using the same data to estimate the transition kernels by solving the ridge regression, right? So when both of these two terms are depending on the same random data, and we cannot take expectation for both of them separately and hope that nothing bad would happen, right? And because we are optimizing this, and because they are both data dependent, then we cannot take the inner product of this quantity with every summand that goes into this p hat, right? So that in the tabular case gives us an additional dependence of the state space, and in this case it will give us additional dependence of dimension D, right? But how to prove that I didn't tell you beyond the like a high level like intuitive idea of covering number. And once we have this, to get the full regret, we simply sum the instantaneous regret up over n, and notice that we will be able to bound this with exploration bonuses. So ultimately, we'll have a quantity so total regret will be the sum over this beta parameter multiply with multiply with this b hn sh ah, right? So it will be it will become something. It will become something like this. And for these individual quantities, and we can actually we can by looking at what these exploration bonuses look like, right? We can we can like what we did was to apply Cauchy-Schwarz inequality to make it the sum of bhn square. So this becomes beta square root of n times the sum of bhn shah square, and that becomes something that we can apply, like the bound, the information gain bound from linear bandits that we use. And the key reason why this could work is because this bound is something that we obtain that's independent to the actual choices that are generated by the algorithm. Right, so this bound is always true, and it doesn't depend polynomially on n, and with this remarkable property, we can substitute this into this quantity, and so that we get a total regret bound that matches what we claim here in this theorem. Okay, so that's the structure. And the next thing that we notice is that there are a couple of missing pieces that we didn't prove. So we skip the information gain bound because it's exactly the same as a linear bandit case, and we made some progress in proving optimism. But then what we realized that as we prove the optimism, then we ended up needing the exactly the same bound that we need for bounding this quantity. Okay, for bounding this quantity. So both the optimism and this part of the regret analysis depend on the same quantity, which requires us to bound our p hat minus p s a multiply with some f of like this is a like inner product of this, and this is equivalent to sum over s prime p hat s a f s prime f s prime. Yeah, when this s is really large and continuous, then you can replace the summation with integral. So it always boils down to bounding this quantity. Yeah, it always boils down to bounding this quantity for some potentially data dependent f, and the way that we address this is to try constructing the bound that works for all possible f and absolute value p hat sa minus p sa dot product with f. Yeah, for any f in this function class f, where f is a mapping from state space to some real value, and then we want to construct a uniform convergence bound of the following form. And if we can do that, and we can show that this epsilon is actually, if we can show that this epsilon is of a quantity that's the same as what we have chosen as the exploration bonus, and in addition, if we can verify that this quantity that we substituted here is actually belonging to this function class f, then we can apply this uniform convergence bound to complete the full proof for the regret of linear MDP. Okay, so I hope to explain this logic again, so it becomes clear what needs to be proven and why do we care about such bound. Yeah, and whenever we talk about uniform in theoretical analysis and in statistics and machine learning, it's usually about a high probability bound that needs to hold simultaneously for a family of a bunch of random functions in certain pre-specified function class. And in order to bound this, it requires some kind of a union bound. When f is discrete, then we can simply try bounding every element of it, and then takes a union bound, and that gives a blow up in this epsilon of order logarithmic factor of the cardinality of this f. And when f is continuous, and things become slightly more complicated, and there are techniques to deal with that, and we're going to be talking about one today. Okay, and let's further construct the concrete estimator for this p hat in this instance that we're dealing with in linear MDP. So we are like constructing this p hat, not an arbitrary estimator, but rather mu hat like inner product with phi of SA, and the phi of SA part of it is known, right? Therefore, if we subtract the true transition kernel here, it becomes subtracting the true the true mu parameter like here as well. And we can group these two together so that what we need to bound is really the inner product between this phi SA and the difference of your estimated value and the true value. Okay, so that is why that is the reason why we need this, and by substituting this into the quantity of interest, right? So now let's consider just bounding a fixed v, right? Let's for the moment assume ignore it that f is not f is a big function class that contains an infinite number of functions. Let's first try to construct a bound for a fixed f or a fixed value function that got input into this Bellman backup step, and then by the like simple closed form solution of this ridge regression estimator, we can decompose this into the term that is corresponding to the bias and the term that's corresponding to the variance, where this epsilon parameter is equal to your observed s h plus 1 I. So this is indicator that is 1 at sh plus 1 I and 0 elsewhere, minus the actual probability, minus its expectation, basically, given SHI and AHI. Okay, so this random variable is a zero mean random variable condition on everything that had happened up to this point. Okay, so if we substitute if we substitute this quantity into if we substitute this quantity, if we substitute this quantity into the expression of p hat minus p multiplied with v, then together with the factorization of p hat, then we get this quantity. So this is a quantity of interest that we really need to bound. So ultimately, we want to bound this quantity after taking sup of v, but now let's consider v to be fixed and then bound this quantity alone. Okay, by like this transpose, we can toggle the order of this matrix vector product and move the vector to the other side, and then this becomes these two things multiplying together, right? So notice after the transpose, this is d by something really large, and this v is s by 1, right? So these two things will give us like a finite dimensional quantity, and this one is a d dimension. So together they are yeah, together they will give us d, and it will give us something that's a real value, right? So when you work with functions and matrices, so the good idea is to always keep doing the dimension checks to make sure that you are writing down things that make sense. You're writing down things that are compatible, and this helps me and helps everybody else who deal with matrices and functions all the time to make significantly less mistakes. Okay, so how we can how we can deal with this. So let me erase this part, and so make some space for me to write things down more clearly. So what we can do is to simply substitute this into here. Wait, there is. Okay. And this becomes phi of SA transpose and lambda HN inverse minus lambda. So both these have this lambda inverse, so I'm extracting this out. And also because this is a symmetric matrix, when I take the transpose, when I take the transpose, then like it becomes itself. Like since it's symmetric, the transpose doesn't matter. And this one will have the mu h star. So I'm doing nothing fancy, but rather substituting this into the expression that of interest below. And then we have this summation term of phi hi s and epsilon I transpose. Notice I'm just doing transpose. Yeah, because we're adding the transpose here, so we toggle the order and then transpose every element, and lastly this got multiplied to v, right? And if we apply like absolute value, so let's say that this quantity is star, then the absolute value of star is smaller than we can apply the triangular inequality of and now we can apply the triangular inequality, and for every such terms we are applying the where we're splitting this into half and half, and then apply the standard Cauchy-Schwarz inequality, right? So this becomes the phi of SA measured in the norm of n minus 1, and minus lambda mu n star multiply with v measured also in the measured also in this norm, right? Again, let's do the dimension check. This is d by s, and this is s by 1, so we end up getting a column vector, and this column vector is taking this this particular ellipsoidal norm, right? So this becomes a bias term, the upper bound for the bias term. For the second term, what we'll get is again, so there's there's also this term that's around. So we'll have this using exactly the same logic. We'll bound this with this quantity, and for the remainder, which I mean it is this remainder. And it becomes the sum of I from 1 to h minus n minus 1 phi of s hi a hi epsilon I transpose of V, right? So let's put this in here, and due to the Cauchy-Schwarz inequality and the splitted matrix in the middle, so this norm is also this lambda n h minus 1, n minus h n minus 1 inverse. Okay, so then it boils down to trying to bound these two quantities separately. For the bias term, so this is bias. So bias term, it is like first of all, I wanted like maybe using a different color could help to clarify things a little bit more. Okay, so first of all, I noticed that this is exactly what we want, right? So these terms are exactly what we want, because we want to bound this using the exploration bonus, and these are terms that are coming from the exploration bonus, right? So no, this is a term that we exactly what we want. All we have to do is to bound the remainder and call them this this beta parameter. Okay, and what we can do is to simply apply the most trivial bound possible for this term. So this bias is this term. This is a bias, but this term is smaller than lambda. So I can extract a constant lambda out. I can, since this matrix has a plus lambda I, so we know that this matrix has a operator norm or spectral norm has the largest singular value that is smaller than 1 over lambda. I extract this 1 over lambda here, and then what we need to what we need to deal with is only the size of this vector, and the size of this vector is smaller than each coordinate of this vector is smaller than h, because this v has L infinity norm of h, and by multiplying this v with every row of this mu n, every row of this mu n transpose, then we get a factor of h, and then so this is a mu n star v 2 norm, and since this smaller than h, and we can bound this by first of all, these two lambdas cancel out, square root of d times h. Since every coordinate of this is smaller than h, and this mu this mu n this mu n is part of what you what you use to construct the transition to construct the transition probability. Therefore, every row of it sums to 1, and then you can get every coordinate to be smaller than h, and ultimately you get a bound of square root of d times h. Okay, for this term, for this term, this is a variance term, and what we're using is this like powerful technique of martingale concentration with a sort of self-normalization, right? So we use exactly this technique in linear bandits, and we're applying this here as well. And this is a martingale because it is a summation of martingale differences that are conditional on everything in the past. It has a 0 mean. And the fact that it is a martingale not like allows us to deal with the filtration and the fact that these random variables are not IID, right? And by this we can we can bound the second part of the variance term with 3h times this log information gain, log determinant of h minus 1 over determinant of lambda 0, and lambda 0 is simply the lambda times identity, right? And this can be bounded in ways that are completely independent to Sn and An using the information gain lemma, so that you get square root of 3h times square root of d log n, yeah, at least on the same order. Okay, so we emphasize that in the bias part, we actually use no other properties besides that this V is pointwise bounded by H. And this is actually ensured by the algorithm. This is ensured by the algorithm with a clipping at H, right? So this term, there are no issue with probabilities, and we do not need to worry about it because it applies to all such V's simultaneously. What we need to worry about is the second part, because in the analysis of the second part, we actually make use of the fact that this V is a fixed quantity that are given. V is fixed rather than random. When V is random and this randomness is correlated with this epsilon i's, then we cannot apply the same martingale bound because it's no longer something that we can bound it. Well, we can bound it using the same theorem. Okay. So it remains for us to deal with this quantity, but with a supremum in front of it, taking over this choice of V. Right. So that motivates us to consider the following problem: sup of f summation of phi s I epsilon. So it's epsilon I transpose with f, right, and measured in this norm of n inverse. Yeah. So this is a quantity that we need to bound. Okay. So the idea is that how we can apply this this result for a fixed V, right? So we still want to use the union bound argument to somehow address this. So the idea is to discretize the space, right? So let's say that this is a set of functions f, and the idea is to cover this function with a bunch of overlapping balls, and so that for every for any f inside this function f, so by the way, after we construct these balls, we take all the center of these balls and collect all these centers into a new function called f epsilon. Okay, so f epsilon is a finite set. It's a discretized version of f that satisfies that for any f, for any function in this function class, there exists like f tilde in this discretized set, such that f minus f tilde pointwise is smaller than epsilon. And what this L infinity norm means is that sup over all the possible input of f, x minus f tilde of x, absolute value is smaller than epsilon. For instance, if this is a function, so this is function f, then an f tilde can be, say, can be a complicated function as long as the largest gap, between any 2 points on f and f tilde are bounded by epsilon, then this is fine. Okay, so you can think about this epsilon as a radius, as this little ball, so that whenever we pick any point within this set, there always exists the center of this ball that contains this f. right? So in this way, we can discretize the space and then work with a finite discretized set of this function space. Okay, more formally, we define this n epsilon to be the number of balls needed to cover F, such that F minus F tilde smaller than epsilon for any F exists F tilde in F. Yeah, so this is a definition of cover number. Okay, and our idea is to work with this covered set, apply the pointwise convergence bound, apply this bound for a fixed V, and let's apply this bound to every single element in this FC epsilon set. And once we do that, we can leverage the similarity of this F tilde, this constructed F tilde with any possibly data dependent choice of F, and then show that they are similar, right? And in this way, like, we can decompose the bound that we need into two terms. One of the term depends on this epsilon, and the other term depends on the uniform convergence bound for this discrete set, which we do have known techniques to deal with. All right. So so how do we what is a kind of function that we need to define? So I argue that the kind of function of interest is of the following form. So why is that? So let's go back a little bit to the algorithm, right? So notice that the kind of function, the kind of function class that we need to specify needs to be one such that no matter how the algorithm has rolled out, no matter what the input to the algorithm is, and this function needs to be inside this function class. And how is this constructed? Right, it's constructed from the previous iteration of the optimistic value iteration, and this is the equation that you use to construct this V. So VH plus 1 hat is equal to some exploration bonus. So this is exploration bonus of VH and BH plus phi SA, but phi SA got multiplied with mu, some mu hat, and then VH plus 1, right? And if we group these two together, we've seen this multiple times, and this gives us this gives us an R to the D, right? This gives us an R to the D, and these two together contribute to this W, right? And moreover, like, this is the expression of Bn, right? So that's how we construct this function. And this mean over this quantity, and this is H. Okay, yeah, sorry, I forgot to max over A. Right, so there's a max over A, and there's a mean by clipping this value at H. Right, so essentially we are trying to enumerate all the possibilities of what this V function could possibly be, and then construct this function class, such that, and the key is that for any realized trajectories that in the algorithm roll out, this V hat must be a subset of this function class F. Okay, and then by looking at this expression, we, as long as we can specify this constant L and B and lambda parameter, and this lambda parameter is clearly coming from our regularization of this lambda, right? And then we have a generic function class that we can later hope to cover. Okay. Yeah. So in the next slide, I'll be deriving the covering number for this class without without choosing these parameters, and then I will be like choosing the particular parameters of L, B, and yeah, we already know what lambda to choose for choosing this L and B. So to construct a particular quantity that we need to prove. Okay. Well. I remember I had a page written about okay, maybe let's just do this. First of all, we'll state the lemma, right? Lemma. So the lemma says that the n epsilon of the Euclidean ball such that the Euclidean ball smaller than B, right? So the covering number of the unit sphere, right? Of this of the hypersphere, hyperball, like the ball of the radius measured in Euclidean distance B, is proportional to the order of 1 over epsilon to the d, b over epsilon to the d. Okay, so this is a lemma, right? So you can get this by applying the formula for the volume of this this ball, and then dividing that by the volume of the little ball that you're using to cover this, and you can get this quantity. Okay, so now I'm gonna try applying this and derive the covering number for this this function class. Okay, so what let's see if I have that page over here. So let's consider like a given let's consider a given function f inside the aforementioned function class that are specified by this w and w and beta and lambda, right? W, beta, and lambda. And let's say that we also have a have a cover set that f hat is in this discretized set of f of epsilon. So since we're measuring the distance in L infinity norm, it suffices for us to consider consider any input s, right? So as long as we can provide a bound for any input s, then the bound would suffice for our purpose, right? So the idea is very simple. It's simply by substituting the definition of this f. So this is smaller than max a w right? I'm just writing the definition and minus so let's say the parameter of f tilde is w hat beta hat gamma hat, right? So this is parameters of f tilde. So following the same definition, you will just have right, and then well this is a norm, and we can extract the maximum out, right? We can and obtain an upper bound, and then we can apply triangular inequality to bound every one of these pairs separately. Okay, so this is smaller than max of A. Well, W minus W hat transpose phi of S A plus max of A. So this is a remaining term. Yeah, this is W hat, beta hat. So we will have beta minus beta hat. But the second term is also different, right? The second term is also different. So we can address that by just adding a term with beta hat, but with the same second term, and then subtracting that term away, and then write a three term like triangular inequality decomposition, right? So this gives phi S A plus max of A beta hat. So now the only things that are different are phi SA hat this is lambda hat phi SA minus square root of phi SA lambda inverse phi SA. Right, so these two are grouped together. So what I'm doing is just to decompose them into three terms, and in each one of the term, only one of the parameters is different, and all the other parameters are the same. And now we can apply the standard Cauchy-Schwarz inequality, and then bound the first term by W minus W hat to and beta minus beta hat, and we call you have this and also the square root, and notice that this one is regularized, so the maximum eigenvalue, maximum singular value of this this lambda inverse matrix is smaller than 1 over lambda, so the square root of that is 1 over square root of lambda. So yeah, actually this beta is a scalar, so I can use absolute value rather than the norm, and this divide by square root of lambda, right? So without loss of generality, so let's assume the feature vector phi SA is smaller than 1. Okay, let's assume this is the features are smaller than 1. I think you actually don't need it. Oh yeah, you don't need it if phi SA is part of the data set. Otherwise you do. And in the third term, so what we can do is to what we can do is to use this like trace inequality. So let's say that you have this matrix A and X transpose A. So this is a quadratic form, right? You can rewrite this to be the trace of X transpose AX, and then this becomes a trace of A XX transpose. Because for trace, you can move things around. You can move this X transpose to the other side by following the same clockwise or anti-clockwise manner. And this becomes the and then you can bound this using like using the standard Cauchy-Schwarz inequality, because the trace is equal to the element-wise element-wise inner product of this. So this is smaller than A's Frobenius norm and XX transpose Frobenius norm, right? By using this argument, then you can move these you can move these two to the other side and then group the differences of lambda inverse together, and you can get a beta of a square root of lambda inverse minus lambda hat inverse from Frobenius norm. Okay, so what this is doing is that in the space of in the space of Frobenius norm, so you can construct this covering set by consider this to be a product of the cover of W, product the cover of the cover set of beta, product a cover set of matrix lambda inverse, right? And the radius of this is three like covering set of the vector spaces actually gives rise to a description of a cover set of the function. And by this derivation, if we can bound this by 1 over epsilon, bound this by epsilon over 3, and epsilon over 3, and epsilon over 3 as well, then altogether this gives me epsilon, right? So to say it differently, we can construct f of epsilon to be the set of function f w beta lambda such that I can such that I can use the product space of W in W epsilon 3 beta in capital beta epsilon 3 and lambda inverse in capital lambda inverse epsilon over 3, right? In this way, whenever we have a f in the original space, then we can try to find the closest closest parameter pointwise within all these three categories, and then construct the one function within this discretized space. And the total number of elements in this function, right? So the f epsilon, and this becomes a covering number of epsilon, is also equal to the product of number of epsilon 3 covering number of W and multiply with n epsilon 3 covering number of this beta set. So this is a cardinality of beta W, cardinality of beta epsilon over 3, multiply with the cardinality of lambda inverse over 3. Now is the time to apply the previous lemma. So notice that all these are Frobenius norm, like absolute value, and Euclidean norm, right? So they're all Euclidean norm if we vectorize these matrices, and then we can just apply this lemma, right? And by applying this lemma, we can choose this epsilon in any way that we want, and then with a carefully chosen the B parameter to tailor to the specified input space. Okay, and the product of these numbers, what are they? The product of those numbers will be proportional to 1 over epsilon to the power of 3D, right? Like essentially the same as that's exactly what we want, right? So that will be the size of the covering number, covering number of the original function class of interest. Okay, so yeah, just to make sure everything is is concrete. So after we've gotten this this covering number calculation, like how can we apply this to how can we apply this to the uniform convergence bound that we're hoping to get? So first of all, what is it that we're trying to get? We are trying to we're trying to bound this quantity, right? So this is what we're trying to bound. So let's copy this over and then write it down. Of f in the function class, phi sa. I remember there's a summation somewhere. Okay, I see. Summation phi SIAI epsilon I transpose f. Right, so this is a quantity that we are interested in, and we have this lambda h n inverse. Right, so this is what we're trying to bound, and what we can do is to to decompose this into f minus the corresponding, like we can subtract the corresponding f tilde within the discretized set, and then add this f tilde back. And by triangular inequality, and this is smaller than yeah, I'm just gonna write phi I to be to simplify the notation a little bit. F minus f tilde. I'm going to just write this rather than just writing out everything. So of f, and the second term is actually completely independent to f. Yeah, but actually it depends on f because f tilde is chosen as a function of f. This one is chosen as a function of f. So let me make it more explicit. So then we'll have f tilde, right? And this is so let's now deal with the two terms separately. For the first thing, that we know that there's always a function f tilde that is epsilon close to f. So we can bound the first term using so we can bound this difference pointwise using epsilon. On the other hand, what is epsilon I? So epsilon I is this one hot function minus its expected value, and its expected value is a probability distribution, so it's sum to 1, and this is obviously sum to 1 because only one of the non-zero coordinates is 1 and all the other coordinates are 0. So epsilon 1 has a 1 norm that are smaller than 2, right? Now this term f minus f tilde has an L infinity norm that's smaller than epsilon. So these two together gives this scalar value of 2 times epsilon, right? So you can bound the first term by extracting the two epsilon out. And what remains is to the sum of lambda I, phi I, like this matrix inverse. Okay, so how can we deal with this? Right, so we could, for instance, just do the most crude things ever. We can apply the we can apply the triangular inequality by just extracting out the summation. Then this becomes square root of phi I transpose inverse phi I. And then we can apply Cauchy-Schwarz inequality. So it becomes the it's smaller than n. Then summation of phi I. Okay, and what is this? And recall that this lambda I is constructed by sum of phi I transpose plus lambda I, right? And j from 1 to n, right? So these phi i's are actually part of this data set that allows us to construct this. So in other words, this is what statistician knows as a leverage score of this data point phi I, right? Like modulo this additional term that makes things only smaller, right? So leverage score is always smaller than it's always smaller than 1. So in total, this is smaller than n, right? Square root of n times n, right? You can also bound it in a different way, but yeah, we could get a bound of n here, right? So in other words, the whole thing here is smaller than 2 epsilon times n. How about this term? This term, you can rewrite this to be the sup of f tilde, because this is always something that's inside the f tilde. No matter like what the mapping from f to f tilde is, so it doesn't really matter if you can just take it out. And now we can apply union bound. The pointwise result for fixed, and now they're only like ne, they're only the covering number of such fixed f tilde, right? And then apply union bound. Right, so you'll end up getting your let's go and check what those pointwise bound look like. Yeah, so this is what the pointwise bound look like. You have this quantity of interest, and then you have this 3h times d log n. Right, so what's your what you get? Yeah, so what you'll end up getting here is is just the d square root of h log yeah, actually I think it's h square root of d log n plus log of n e over delta, right? So this term is coming from the taking the union bound over ne discrete variables, and the only like so the first expression allows us to choose what this epsilon is. So since this is 2 epsilon n, it suffices to choose epsilon to be it suffices to choose epsilon to be 1 over 1 over n, and this is in a and this is only in the logarithmic factor, so everything is okay. So you can substitute this into this covering number bound, and then altogether you will you'll end up getting the quantity that we're hoping to prove. Okay, so I'm not gonna bore you with detailed calculations, but I hope I've illustrated the idea of how to derive this uniform convergence bound like clearly, and for details just take a look at the textbook, and there are like many logarithmic factors that you have to keep track of to get this quantity. Right, so these are the like overall picture of how you end up getting this complicated looking expression that happens to work. All right. All right, so before I wrap up the section, I wanted to say a few last words about the linear MDPs and about the chapter about exploration. So first of all, I think linear MDP is a pretty good model. It is good because it is like not completely parametric. The model, the Markov decision processes is actually described by an exponential number of parameters, d times s. So this is to describe this mu star parameter, and the thing is that you don't actually need to collect that many samples, and you don't need to estimate this parameter well in order to learn how to make the right decisions in linear MDPs. Yeah, to say it differently, like on the high level, this is a sequential decision-making problem, and you don't need to have the full information of how the world works before you can make the right nearly optimal decision. And you only have to sample, and you only have to sample a very sparse number of instances, and those are sufficient for you to behave nearly optimally. Right. So from that perspective, so even though the assumption of linear MDP is still quite strong, but it is a remarkable result. And the second thing is that so this is still a pretty active area of research on extensions of linear MDPs. So in particular, people could ask the questions: what happens if phi is unknown? What happens that there exists such a linear representation, but you just don't have access to it? Can you use a deep neural network to parameterize a family that contains the one that is linear and then do end-to-end representation learning? Or what happens when you're like a related question is what happens you do not actually have a linear representation, but rather it follows from some nonlinear form from this feature to construct this this transition kernel. Yeah, and in that case, what are the things that you can do? Another somewhat technical issue is that when you directly convert the results, the best result that people have obtained for linear MDP to the tabular setting, so remember that linear MDP is strictly more general than the tabular setting, because you can write the tabular setting as a special case of linear MDP with a specific chosen like feature map, and with specifically chosen the file phi star, a mu star. Then the direct application of the optimal rates in linear MDP actually leads to suboptimal dependence on the dimensionality, or in the tabular case, state space. So basically, when you do the naive conversion, and D is equal to S, and the results of linear MDP typically depends on D square root of S, but the optimal rate in the tabular case is the square root of S times T, where this T is number of steps, or number of episodes, right? So you're resulting a square root of S additional dependence on S. So this problem is also like not resolved. Now, can you come up with linear MDP analysis that are in some sense adaptive, that adapt to the instances of the sub-problems within linear MDPs that can be proven to learn even faster than the worst case? Okay, so I think it's a good time to take a break. So we will resume in 2:30, and in the remainder of the lecture, I'll give you a short introduction to offline reinforcement learning, and then talk about off-policy evaluation in bandits. Yeah, actually it's 3:31. So let's resume the lecture at 2:31. All right, welcome back, class. Well, I hope you managed to get refreshed with water and maybe snacks. So as I said, in the remainder of the class, I'm gonna be talking about where we're moving into a new chapter, and I'm gonna be talking about offline reinforcement learning. Okay, so recall that reinforcement learning is like one of the hottest topics nowadays in machine learning. And a lot of that is driven by the promise of future applications of these techniques for sequential decision making and for learning policies that can actually interact with the environment rather than just passively observing and predicting what's going to happen in the environment. Okay, in the standard reinforcement learning setting, an agent need to interact with the environment sequentially and learn from feedback, and then update the agent's policy and so on. And then access to an environment with online access is critical. However, in real life, like when a lot of the promising applications that people intend to use reinforcement learning for are actually cases where it's difficult to have such online access. For instance, in personalized medicine, you cannot actually just explore by feeding the different treatment plans and then drugs to a random to a random patient unless this is a approved clinical trial. But like using reinforcement learning with sample complexities that are that depends on the dimensionality and even the state space. That's there's no way that FDA is going to approve such large scale experiment. And there are many other cases. Say in self-driving car, you cannot arbitrarily explore like running down the cliff and crashing is not a good way of learning policy. And you don't have to go down that path to collect a big negative reward before you can realize that the policy that drives you down the cliff is a bad policy, right? So in many real life applications, we don't actually have access to such online access to the environment. Sometimes we don't even have access to a simulator. So even if we do have a physics-based simulator, so sometimes running those simulators can be costly, and efficient approximation of those simulation schemes will result in something that's very far away from the reality. There are safety legal issues. There are large state space action spaces, partial observation, and long planning horizon, and so on. So these are the challenges that makes reinforcement learning um, 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 hard to like use and deploy in practice. In reality, what like if you join a company and work on a machine learning project, so what the typical situation that you have before you actually come up with an agent to interact with their user data is that you're given this big data set already. So these are collected from like version 0.7, 0.8, and 0.9 of our software, and these are their outcomes, and the way that our as some of these data are collected by human operators, then we don't exactly know how they are making their decisions on which product to show. And yeah, we have everything that's summarized in this big table, right? Can you bootstrap from this? And please make sure that you come up with something that's better than what is deployed before we can try yours on our production environment, right? So these are the situations that the software engineers who know machine learning and wanted to have a dent in practice experiencing every day, right? You cannot actually just design something and then tell your manager that, trust me, let's ship this and this will be great. And at the beginning, it probably won't be great, but give it time and it will learn, it will improve itself, and eventually it will be great. right? But that's simply not good enough. So that motivates the problem of so-called offline reinforcement learning. So in the online reinforcement learning, you keep taking actions and receive state transitions and reward as a function of the current state. And in offline reinforcement learning, you basically have a bunch of data that's in the form of SAR. With I guess maybe n copies of the SAR and S prime with n copy of that that's collected from drawn from maybe a different policy. Sometimes you know the policy, sometimes you don't. And once you have this data set, and then the agent is supposed to come up with a new policy that is better than the old, and then possibly getting a nearly optimal policy with only locked data. Okay. And as an example, so in a simplified model, let's consider the recommendation system. And if the company is recommending the item to users and users are deciding what to buy or not to buy, you can model this as a reinforcement learning problem, where these recommendations are the actions that are taken, and then the clicks of the users and the purchase decisions of the users will be the feedback that you provide to the learner. And whenever you ship a new recommendation engine, like maybe you have to first evaluate it using the data that's already there, and applying your new recommendation to the old data will suddenly run into the situation that you will recommend something that hasn't been previously recommended to that particular user. So maybe what you recommend has been recommended to a different user, but that's a completely different context, and why should it apply? And maybe your recommendation has an effect of changing the distribution of your users, and some users will like it and they will stay, and they may even attract more people more similar to them. But once it stabilizes, then the stream of sessions with people exploring your website trying to buy stuff will be maybe different, and maybe that's a function of your policy of generating this recommendation in the first place. First place. Yeah, so the two goals of offline reinforcement learning, also known as off-policy learning, is to evaluate new algorithms without actually running it, and to learn like a better algorithm without interacting with the world. Okay. So there are two typical settings of policy evaluation and of policy learning. Like I said, in off-policy evaluation, we consider a fixed target policy. And the offline data are collected by running a different policy. That's why it's called off policy, because pi and mu, they are different. And like the evaluation itself is a research topic. So in online, when you have online access, this is straightforward, right? So in online environment, in order to evaluate this policy mu, and you can simply run it. You can simply run it and then take averages, and that becomes a valid and a low variance estimator of the value of this policy. But in the offline setting, like even these simple problems become like somewhat more challenging, because the pi and mu, they are visiting the different, very different state distributions. So the occupancy measure that's induced by pi and mu, they will be very different. And offline learning is even more challenging. So this is about coming up with algorithms that bootstrap from the offline collected data with some policy, and then try to find the optimal policy right away. So that categorizes the sequence of lectures that I will be given until we move into the project presentations. So we'll talk about the off-policy evaluation problems or offline policy evaluation problems first on the various models, and then we'll move to talk about the algorithms that deals with offline policy learning. And we'll again, like, some of these will be algorithmic, and other part of the lectures will be will focus on like deriving provable guarantees for these algorithms and working out what is the sample complexity, how large such offline trajectory data set needs to be before you can find an epsilon optimal policy, like as an example. So these tasks are related to each other via the so-called uniform convergence in off-policy evaluation, right? So the idea is exactly the same as the uniform convergence that we talked about in the earlier part of the lecture. And the key challenge of not being able to use the same data to evaluate this policy is because this policy is chosen from the same, like it's selected by optimizing certain performance metric on the same data set, right? Naively, like running OPE method on this on this target policy on this offline data will necessarily result in optimization biases and which makes the results of your evaluation unreliable. On the other hand, if we can simultaneously evaluate a family of policy and which always contain this optimal policy that no matter how your algorithm is running the selection, then that becomes a conservative upper bound of the error that we can derive for this data-dependent choice of policy. Okay, we'll get into more of that as we get to the offline policy evaluation part of the lectures. Okay, so for today, we're going to be focusing on so yeah, the lecture will be like another 5 minutes. We'll be focusing on this simpler model in between multi-arm bandit and reinforcement learning. So we consider the context or the state where we're using X rather than S to be consistent with the typical choice of these letters in supervised learning. So in supervised learning, X is typically the feature vector. So we're adopting this because this is the same assumption as in supervised learning. So X is drawn IID from possibly R to the D, and the actions. Let's say the action is a discrete set, and it doesn't have to be discrete, but if it is, then this is a discrete probability distribution given X. And your login policy samples this action by drawing from some distribution, conditional distribution mu of the action given the context, right? So this could be your recommendation engine, and this is item that you recommend, and this is the feature of the web session and the user's profile and everything that you hire engineer to do heavy-handed feature engineering and create these very informative features. And the reward is drawn from some distribution condition on the context and action, right? So this is a probability of whether this user will click or not click on this advertisement. And if you click, then you get a reward of 1, otherwise you get a reward of 0. And we can similarly define the value function in the same way that we define value function before. So this is the expected reward of running a particular policy, right? So the value of policy mu is the expected reward, like over the randomness of everything, and then the kind of data sets that we collect is a triplet in terms of state action rewards. There are no state transitions here because this is a bandit model, and in all bandit models we decide to simplify it and ignore the state transitions. So no matter what actions that you pick, no matter what policy you run, this distribution of the context is arbitrary and unchanged. It remains independent and identically distributed. Okay, so that's a setting. And in off policy evaluation, we are hoping to use the aforementioned data collected by running the login policy mu to estimate the value of the target policy pi. Okay, so this is what we're going to be focusing on. And sometimes you get the reward. You also so sometimes you don't have access to the login policy mu, but rather you have access to the sequence of probabilities. So by propensities, I simply mean the probability of choosing action AI. So the data set can be xi, ai, ri, mu I. Right? Sometimes you have mu I, sometimes you don't, and when you have access to mu as a function, then you don't need to have access to mu I, right? So, but when you don't, sometimes it's better to have some log probability in that big data table that I showed you just now. This is closely related to the problem that people, statisticians and econometricians has considered in the causal inference world, and it is mathematically equivalent to the average treatment effect estimation. And to map the semantics out, the actions corresponding to choosing treatment 0 or treatment 1, the reward is a response variable, and the context is just a covariate of the patient and the particular disease. Okay. So let me just spend the next 2 minutes talking about like 2 ideas how we can derive algorithms for off-policy evaluation in this setting. So this should be familiar to you. So recall that comparing to the reinforcement learning setting, we are really not making very strong assumptions on the discrete space, on the discrete action and discrete state, right? Therefore, it's unclear whether we have access to a function class that can approximate the expected reward well, right? Because this is a mapping from R to the D to some real value, and it could be arbitrarily complicated. Okay. On the other hand, like we can always try to fit a regression model. Say we can fit a deep neural networks and make use of this state and action pair to try to predict the expected reward. And since we're collecting all these data with a bunch of X and A, and those are the training data that I can use to construct such estimator. And once I have this, and then I can plug it into the formula of calculating the value of a new policy pi by going over all the input, all the observed contexts, trying out all possible actions in the action space, and then assign the probability of choosing those actions. Right. So this is just a plug-in estimator of if we plug in this regression model into here, and this gives me a single value evaluation of this quantity of interest. How well will this policy pi perform? Like suppose I've been running this in the past. So this is asking the counterfactual question. The issue of this is that this approach like heavily rely on how good this regression model is. If this regression model is biased or high variant, then if this regression model is not able to represent the complex function of this expected reward, then this model will potentially perform very poorly and then leads to high bias. Another idea, which is the last thing I'm going to be talking about, is the importance sampling. So the idea is to use a change of measure. So what you can do is to simply do empirical averaging of the observed reward, but instead of using a weight of 1, so now you like divide the probability that this action AI is taken and then multiply the probability that the target policy would have chosen this action. So in this case, we'll get an unbiased estimator So no matter how complicated this expected reward function is of the target policy, right? So this will work if the login policy is randomized. So it's easy to prove that this is unbiased. So expectation of V pi IPS is equal to, since everything is IID, I can push the expectation inside inside the summation. Ri, and by law of total expectation, I can first condition on x1, right? Since I is IID, these two got canceled out, right? I can condition on x1 and then consider the expectation of the conditional probability distribution. But the conditional probability distribution of choosing this action is simply summation over the action of mu of A given x1, and then you will have pi of A given x1, mu of A given x1, and these two got canceled out, and multiply with the expected value of Ri given S and A, right? And this becomes this becomes the value of the target policy pi, right? So it's a simple change of measure trick, which will work. So there are no assumptions that's needed on the reward. Okay, so I'll stop here. In the next lecture, I'll talk about these important sampling estimators more carefully, and then how they are connected to the regression-based estimators when we have access to a function class that's actually realizable. I'll also talk about how to generalize this to the reinforcement learning setting, and talk about the theoretical analysis of these methods. Okay, so I'll see you guys on Wednesday.